So today we're going to talk about logarithms. All right. So, whoops. Okay. So let's talk about what a logarithm is. Okay. So look, suppose you have, we're writing the powers of 2, right? 2 to the 1 is 2. 2 squared is 4. So I'm basically just increasing the power, the exponents by 1. I increase by 1, 2 to the power of 3, I get 8. But look at what happens. In going from 2 to 3, I increase the exponent by 1, but the powers went from 4 to 8. So I skipped all the other numbers, right? Like 5, 6, 7, and so on. So what if I wanted to know what should be the exponent of 2 that would give me a 6, right? Well, the answer to that question is a logarithm. So another way I can ask that is, what is the logarithm, and then, right, of this situation? And then you would say, well, blah. So for example, you know how 2 to the power of 3 is 8? Okay? I can say, what is log base 2 of 8? Just like that. And if I were walking down the street and there was a billboard and all it said on the billboard was log base 2 of 8, I would say, oh my God, someone's looking for the exponent of 2 to get an 8. And what would that exponent be? 3. So the answer to this would be a 3. That is the exponent, right? So that means the answer to a logarithm is always an exponent. Okay? So now, let's look more at what powers look like. So take a look at this one. B to the y is equal to x. B is the base, right? And y is the exponent. So when I write it in terms of a logarithm, it's log base b, that's the base, of x equals y. That is always the exponent. So the logarithm always equals a what? Exponent. Okay, so, all right. What is a logarithm? An exponent. Okay, good. So take a look here. We're just going to rewrite these in exponential form. So this is a logarithm. The answer to a logarithm is always an exponent. Every exponent needs a base. What's the base here? 3 to the power of 2 equals 9. That's it. We just rewrote that logarithm. Okay, here. Exponent, base. 10 to the negative 2 equals 1 over 100. Here, exponent, base. 3 to the 6 is 729. Okay? All right. Next one. Write each equation in logarithmic form. So take a look. Here we have the exponent, and here we have the base. So it's got to be log base 5, 125 equals the exponent. A logarithm should always equal the exponent. So what would the next be? What would the next one be? Log base of 3 equals a third. Correct. What about the next one? Fabulous. Okay. So here, let's evaluate the expression. Evaluate means find the numerical answer. So here we're looking for the exponent of 2. That gives us an 8, and that would be 3. What about this one? So the way in which we're going to think about that is, this is the base, right? 25 to the power of what is 5? Yes. So when we're dealing with this, we're talking about exponents, which are the same as roots sometimes. So let's think about it this way. What can I do to 25 to get 5? You should only think of like roots or exponents. Root 25 is 5, right? So it's 25 to the half. Okay, kind of, but it's like, it's trippy. It's kind of trippy, yeah. So 4 to the power of what gives you 64? 3. So x is 3 for this one. Okay? Here, 6 to the power of what will be 1 over 36? -2. Yay! Your very first logarithms. Isn't that exciting? Okay. It really doesn't get that complicated. If we do it correctly, it won't get too complicated. Okay, so what about this next one? 1 over 9 to the power of what gives you 1 over 81? 2. Yay. All right. Okay, what about the next one? Okay, so the next one, 10 to the power of what gives you all these zeros? Right, so what I would do is just count the zeros. How many zeros are there? I think there's 5. So 1, 2, 3, 4. I know it's tricky. I really have to like concentrate. So x is equal to 5.
So you don't count how many tens of zeros.
Right, you just count the number of zeros here. And then, so if you were going the other way, like log base 10 of 0.0001, now we count how many decimal places total. So 1, 2, 3, 4, that would be -4. Okay? All right. So the Richter scale. You guys heard of the Richter scale? It's how they measure earthquakes. So the Richter scale measures earthquake intensity. The increase in intensity between each number is 10 times. So for instance, if you have an earthquake with a magnitude of 7, that's 10 times more intense than an earthquake measuring with a magnitude of 6.
Is that actually true?
It is true. It is so true. I mean, it is math. So if you have an earthquake, so the intensity is like the level, like, you know, it's like how, right. So so if you multiply the intensity by 10, like it'll go from a magnitude of 3 to a magnitude of 4, right? So to go from a magnitude of 3 to a magnitude of 6, 4, 5, 6, that's 1,000 times more intense. That's why a magnitude of 3, you're like, oh my God, wasn't that fun? Did you feel that little, you know, whatever last night? But then a magnitude of 6, I mean, there's like cities devastated, right? So, okay. So, I mean, a 7 is, okay. So, the intensity of an earthquake can be modeled by this. Oops, didn't mean to do that. This, where X is the Richter scale rating. Okay, so the largest recorded earthquake in the United States was a magnitude 9.2. Okay, that struck Prince William Sound, Alaska, in 1964. So this should say use the information at the top to find the intensity. Okay, so let's look at this again. This is the equation for the intensity. That means this is intensity, and then X is the Richter scale rating, which is the magnitude, right? So here we're looking for the intensity. So it's going to be Y equals 10 to the power of X minus 1. Y equals 10 to the power of 9.2 minus 1, which, you know, we're not going to do by the hand, right? You have to plug that into your calculator, and it's a heavy duty number. It's 489,000. Oh my goodness, sorry. 489,319.246. So that's the intensity, okay? Yeah.
I know my calculator, 10 to the power of 8.2, right? When that,
Mm-hmm.
it gave me 1.584.
To the power, but then is there an E, blah, blah, blah? Yeah, so that means times 10 to the power of 8, right? So that's in scientific notation,
Yeah.
1.58 times 10 to the power of 8.
So how would I write that out, like with the decimal?
Oh, sorry.
Would you allow it in scientific notation?
So no. Okay, so here, let's take a look. So this is going to be 10 to the power of 8.2. So mine gives me the full amount. I'll take a look at your settings in a minute. Okay? Okay, I'll take a look at the settings and I'll tell you guys.
Can I see the phone number?
Okay.
What you can do, if it just copy the answer and click enter.
Right, that's also one way, but later on I'll do it. Let's not mess with it now. We'll do it later so you don't have to do two steps. Okay, write an equation of the form y equals log base 10 of x plus c for the inverse of the function. So this is the inverse of the function up there. What was the function? Right. So remember how we find inverses. First thing is interchange x and y, okay? So change x and y. So this becomes x equals 10 to the y minus 1. Okay. Now we have to solve this for y, which is all the way up there in the exponent. So what you want to do now is you want to rewrite in logarithmic form. Okay, so where is the exponent here? Y minus 1, correct? What's the base? 10. So this is going to be log base 10 of x equals the exponent. A logarithm always equals the exponent. Okay? All right. But now what are we going to solve for? Y. So log base 10 of x plus 1 equals y. And then to make it an inverse, we say f inverse of x.
Why is it log?
10. Okay.
Why is it
Huh?
why is it
Wait, so is one technically C then? It says y log 10x.
Right, right. So remember, this is the exponent and it has to equal the logarithm. Okay, so that's that. This one's even quicker.
Wait, can you go back?
Okay, for a second. Okay, this one's even quicker. It's just this page. So here, we're going to solve logarithmic equations basically using the same properties. So here we have a logarithm. Where's the base? 8. Where's the exponent? 4/3. So we say x equals 8 to the 4/3. And I can totally simplify that because I'm experts at the last chapter. This is cube root of 8 to the power of 4. We did it last chapter. So cube root of 8 is what? 2 to the power of 4, 16. Okay. So, so here, x equals base to the power of, the exponent is 3/2, sorry. So x is square root of 16 cubed. Root 16 these days is what? 4 cubed is 64. So always, okay, so here's what you're going to do. First, locate the base. Every base needs an exponent. The exponent is always what the logarithm is equal to. So now you have base to the exponent, and this is this is what they will equal. So let's do this next one. Here is a base. Here is an exponent. So x to the 5/2 is equal to 32. So this is like the one that we did, again, in the previous chapters, right? So how would we solve for x here? Raise both of them to the power of 2/5. So x is 5 root of 32 squared. Okay. So fifth root of 32 is 5. Fifth root of 32 is 2. What I meant to say is 5 2's make 32, right? So this is a 2 squared 4.
For some of these, will be another calculator.
Yes. Okay, so I'm now going to put you on a question quota.
Oh, yeah, I'm sorry.
Okay. Okay. All right. So here we go. Base exponent. Okay, so 1/2 is equal to 8 to the x. All right. So how are we going to solve this one? Well, okay, so now look at the difference. Here, the base was the x. Here, the x is in the exponent. So this is like what we were doing in the homework for today. This, we write it as 2 to the minus 1, and then 2 to the 3x. Remember like what you did for homework for today?
For today.
Oh, so it'll be negative 1 equals 3.
Isn't that what we did last time? Yeah. So negative 1 equals 3x. Huh? It's genius, is what I'm saying. I love logarithms. They're like legit one of my favorite things to do, like ever.
I
Okay.
also love logarithms.
Don't you though? Yeah. I can totally like hear the genuineness of that statement. Yeah.
I know, right?
Okay, so here's another lovely property that I'm not going to dwell on too much. If you have identical logarithms on both sides of the equation, you can set the insides equal to each other. So look over here. Log base 4 of something equals log base 4 of something. When they're identical logs like that on either side, which they're never going to be not identical, right? They're never going to be different. So we're going to set the insides equal to each other. X squared equals negative 6x minus 8. And now this is a lovely quadratic equation like in chapter 4. X squared plus 6x plus 8 equals 0. Factor x plus 4, x plus 2. Now, this is going to be x equals negative 4, x equals negative 2. But when you solve logarithmic equations, you always have to check for extraneous solutions. So here we have to check. Put in the x equals negative 4. We get log base 4. Negative 4 squared is 16. And we want to see, does this equal log base 4? Negative 6 times negative 4 is 24 minus 8. Oh, it's log base 4 of 16. So those do equal each other. So the negative 4, put the negative 4 in here.
Okay.
24 minus 8. Okay, so now go ahead and do it for x equals negative 2. See if it works.
You don't actually
Huh? So let's see if it works for x equals negative 2.
Yeah.
It does work. Okay? It does work. So yes, both of these are solutions. Okay. So let's do the next one. Log base 5, log base 5. Set these equal to each other. And then we get x squared minus, oh, that happened so quickly. Sorry, let's set them equal to each other. Okay, and then this equal to 0, does that factor? X minus 5, x plus 2. Yes. So here I get x equals 5, x equals negative 2.
So if it's prime,
It will probably not be because it'll be something that you can solve. Not really. You won't get problem like that. Okay, so let's check. X equals 5. So I get log base 5. What do I get in the parentheses there? 15 equals log base 5, 15. Yep. Okay, so now let's take a look at the negative 2. Log base 5. So if we have negative 2, what would that give me? 4 minus 10, negative 6, right? Is that right? Okay, let's think about that for a minute. So suppose you have something like this, equals like some number x. This x is the exponent, right? So we're saying 5 to the power of some number should equal negative 6. Is that possible? Can you take a positive number, raise it to an exponent, and have it equal a negative number? No. Right? Like 5 to the power of 0 is 1. 5 to the power of negative 1 is 1 over 5. 5 to the power of 1 is 5. So you can never have log of a negative number. This is not in the domain of the log. So we can just cross out the x equals negative 2. That means the only answer is x equals 5. Okay? Okay. Next one. Solve the following equation for m. Okay. What do you think the first step should be here? What do you think? To solve for m, what should we do first? Let's add 15. Okay. 7 log base 4m. Okay, now I'm going to divide both sides by 7. So what does that equal? N plus 15 all over 7 is log, it's lagging, base 4n. Oh, m. Oh, this is also an m. Okay. Come on. It won't turn into an... Oh, okay. So now, what's the base here? 4. Every base needs an exponent. What's the exponent? N plus 15 over 7. So this is going to be... Come on. Oh, it slowed down. So this is going to be 4 to the power of n plus 15 over 7 is equal to m. There's really a lag. Okay?
How'd you get? Oh.
So you can't simplify it.
That's it. You can't simplify anymore. Yeah.
I have like n plus
equal like this one. When I plugged it into my calculator, I got like giant,
Okay, let's do it again.
like here.
That's so crazy.
That's 6 and 0.
Oh, okay, there we go.
Okay.